In the operation of power amplifiers, there are four classes: A, B, AB, and C. In class A operation, conduction angle is 360 degrees and the operating point is located in the middle or center of the linear region. In class B operation, the conduction angle is 180 degrees and operating point is located over the edge of cutoff region. In class AB operation, conduction angle is more than 180 degrees and operating point is above cutoff, but in the linear region near to operating point of class B operation. In class C operation, conduction angle is less than 180 degrees and the operating point is located deep inside the cutoff region. As you move from class A to C, one can notice distortion increases, efficiency also increases. Class A operation is resorted to in case of audio amplifiers, where clarity is more important. Less distortion is more important. Class B is used when power availability is low, like on-board satellite. Their amplifiers are operated in class B mode. Class AB operation is used mainly to avoid crossover distortion associated with class B operation. Class C operation is used in case of tuned amplifiers. Here, the amplifier's load is a parallel LC circuit. In this mode, distortion is large. Of course, efficiency is also large. Electronic circuits, second part of power amplifiers, a series on semiconductor devices and circuits, lecture number 8.19. Power amplifiers are amplifiers capable of handling high signal powers and high signal amplitudes. There are two classifications. Those classifications are given in part 1. According to one classification, power amplifiers are divided into A, B, AB, C, E, F, etc. Out of these categories, first four, A, B, AB, C. These four categories are considered to be important and popular. Class A operation, Class A amplifiers, they are already covered in part A. In this part, the focus is on Class B operation, Class AB operation, Class C operation. Now we move further to begin the first session. A few points regarding Class B, introductory points. In Class B, only 50% of the input signal is used. The active element carries current during one half of each cycle and is turned off during the other half. This point is not only introductory point but also a point describing the functionality of class B amplifier, working of class B amplifier. The bias point is set exactly or very close to the threshold value for the active device, resulting in a collector or drain operating current, quiescent current very near to zero. It is already mentioned for class A operation, operating point is somewhere here. Class B, it is here. Class AB operation, operating point is here. For class C, it is here. So A, B, AB. The RF input drive waveform will then symmetrically swing about the active device's threshold level, resulting in half of the waveform or 180 degrees conducting to the output. The class B mode gives maximum conversion efficiency of 78.5%. As mentioned in part A, these figures are theoretical maximum. You can have this much larger efficiencies only on paper. In reality, it is not so. Reality or actual efficiencies are quite low. This point has to be kept in mind. Two types are there in class B: complementary symmetry amplifier, standard push-pull amplifier. Before going further, it requires to be mentioned here that class B amplifiers use two active elements, two transistors, either two BJTs or two FETs. In class A, you can find only one transistor. In class B, you find two. One transistor conducts one half cycle, another transistor conducts other half cycle. At the end, we get complete cycle. The outputs of two transistors are combined, resulting in amplified version of the input completely. Now, what is a complementary symmetry amplifier? It uses complementary transistors, one NPN and other PNP, or NMOS and PMOS. As mentioned, class B uses two transistors. One transistor is NPN, other is PNP, or one is NMOS, another is PMOS, in complementary symmetry amplifier. This is also known as push-pull emitter follower and is the most commonly used class B amplifier. The bipolar implementation of class B operation uses dual symmetric power supplies. Now, standard push-pull amplifier. It uses two transistors of same type, either NPN or PNP, with the emitters tied together, same type. It uses a center tap transformer or a transistor phase splitter to feed the signal at the input side. It also uses a center tapped transformer to combine transistor outputs at the output side. The standard push-pull amplifier uses center tapped transformer. Complementary symmetry amplifier uses complementary transistors. Here is shown the circuit of complementary symmetry class B amplifier. Two transistors are there. Notice two transistors. Top one is NPN, bottom one is PNP. Top transistor is biased by positive voltage plus VCC. Bottom one is minus VCC. The input signal, same input signal. it is fed to Q1 and Q2. During positive half cycle, one transistor conducts. During negative half cycle, other transistor conducts. When one transistor is conducting, other transistor remains in a non-conducting state. So at a point of time, only one transistor is in conduction. In B is shown output versus input. During positive half cycle, Q1 is on, Q2 is off. So this is on. This amplifies, Q1 amplifies positive half cycle, Q2 amplifies negative half cycle. Standard push-pull amplifier. Here also two transistors, but both are NPN. Notice Q2 and Q3, both are NPN. And also notice input to Q2 is different from input to Q3. Not completely different. There is a relation between the inputs. Inputs are same except for phase difference of 180 degrees. When input to Q2 is positive, input to Q3 is negative half cycle. When input to Q2 is negative half cycle, input to Q3 is positive half cycle. These inputs with 180 degrees phase shift are obtained from the actual input signal. It is done with the help of center tap transformer. It is not a difficult thing. The outputs of Q2 and Q3, they are connected to primary of a transformer. Load is connected to secondary of the transformer. You can see that output is complete cycle. Standard push-pull amplifier. This is the same as shown in the previous one, but difference is there. The difference is in this configuration, the derivation of two complementary input signals from the input signal is shown. It is done with the help of a center tap transformer. In case of class B operation, collector circuit efficiency is given by this formula. Eta equal to pi by 4, 1 minus VCE minimum by VCC. These symbols have their usual meanings. Class B is associated with certain demerits. What are they? Each amplifier of class B type requires two transistors. Standard push-pull amplifier requires a center tapped transformer which is bulky. It occupies more space. It is expensive too. Class B operation is also associated with one type of distortion, crossover distortion. What is this crossover distortion? In Class B operation, one transistor starts conducting immediately after the other transistor moves into non-conducting state. If a transistor doesn't move to conducting state, immediately move to conducting state after the other transistor goes into non-conducting state, then one type of distortion comes into being. It is called crossover distortion. One can understand crossover distortion with the help of a diagram. This is one cycle. In Class B, one transistor provides amplification, conducts and provides amplification to one half cycle. Other transistor conducts and provides amplification to other half cycle. When transistor 1 is conducting and providing amplification to positive half cycle. Transistor 2, it remains in a non-conducting state and it starts conducting only when positive half cycle is over and negative half cycle is just started. If this changeover happens without any time lag between the changeover, then there will not be any distortion. Otherwise, if some lag exists in the changeover, the output will be like this. You can find some non-conducting states in between half cycles. Notice this signal is not same as the original signal that appears at the output terminals when the complete input signal, both half cycles are amplified. So crossover distortion exists unless proper precautions are taken in class B. Now class AB operation. Some points regarding class AB mode of operation. It is an intermediate between class A and B. The two active elements together conduct more than half of the time period. When moving to class AB mode, the bias point is shifted such that the collector drain current is below half of Imax but above its zero threshold. With this restriction, the input drive waveform experiences clipping of the negative portion of its cycle, switching of the active device. The highest obtainable efficiency for class AB operation occurs when the conduction angle approaches 180 degrees. But then class AB becomes class B. When conduction angle is 180 degrees, it is class B operation. Here is shown the circuit. In class AB mode also two transistors Q1 and Q2. In B is shown transfer characteristic Vi, V0 characteristic. Demerits are there for class AB also. Class AB has come into being to eliminate the crossover distortion. This point has to be kept in mind. Class B is associated with crossover distortion. To eliminate crossover distortion, class AB has come into being. However, the purging of distortion is associated with wastage of power and consequent reduction in efficiency. The efficiency of a class AB power amplifier below 78.5% is usually a little less than that of class B circuit. As already mentioned, class A means here, class B means here, class AB is here. Operating point is in between A and B. When operation is class B, it is 78.5%. Class AB means efficiency comes down. Distortion comes down, efficiency also comes down as you move from B to AB. Some points regarding class C. In class C operation, less than 50% of the input signal is used and active element conducts less than half of the time. When the bias point is lowered further from class AB operation, moving to below the threshold value of the active device, the mode of operation changes to class C. Now only a portion of the positive half cycle of the RF input is conducted across the active device to the output. The range of class C mode conduction angles falls within 0 and pi. In class A, entire cycle, this is A. In B, only half cycle, this is. In AB, less than half cycle, this is AB. Sorry, more than half cycle. AB, more than half cycle. In C, less than half cycle. Full cycle means 360 degrees, half cycle means 180 degrees, more than half cycle means more than 180 degrees, less than half cycle means less than 180. This is class A, class B, class AB, class C in terms of conduction angles. As with the class AB operation, biasing the active device closer to its lower valued conduction angle increases efficiency. Efficiency becomes more. However, in class C operation, this action would completely turn off the active device. It can be found a conversion efficiency of nearly 94% is achievable when biased in moderate class C mode. This class of amplifiers have two modes of operation, tuned and untuned. The tuned circuit resonates at one frequency, the fixed carrier frequency, and so unwanted frequencies are suppressed. The signal bandwidth of the amplifier is limited by the Q factor of the tuned circuit, but this is not a serious limitation. Any residual harmonics can be removed further using a filter. So this is about tuned class C amplifier. Diagram is shown. A tuned circuit is used as load. This is ordinary amplifier only, tuned circuit. Operating point of this amplifier, it is set in cutoff region somewhere here. This is C, this is B, this is AB, this is A. As it is in cutoff. When signal input is given, sometimes this signal input makes the transistor to jump into above cutoff, active region. Only that part of input signal which exists in the active region, only that conducts and hits the resonant circuit into oscillation. Those oscillations are output of the amplifier. Class A applications. These are highly popular with some hobbyists and most of the audiophiles. They are being used mostly for their simplicity, absence of crossover distortion, reduced odd harmonic and higher order harmonic distortion. Notice class A means low distortion, more linearity, less efficiency. As they are more linear, lesser distortion, they are used for amplifying audio signals. These are also used in the development of long-tailed pair, which is not only linear but also efficient. In fact, it forms basis of many more complex circuits, including several audio amplifiers. These are used in almost all op-amps, particularly in the output stages of high-quality op-amps. The reason is distortion, less, very small amount of distortion. These are occasionally used as medium power, low efficiency, high cost audio power amplifiers. In these circuits, the power consumption is unrelated to output power, ultimately leading to low efficiency and high heat dissipation. Now, class B, A, B, C application. Because of their greater efficiency, class A, B power amplifiers are employed more often than class A circuits. As already mentioned, in class B, only one transistor is conducting at a time. When one is conducting, other remains in cutoff. But in class A, the transistor is always in conduction. So efficiency is low in class A. Class AB is an extremely popular amplifier operation and it is used in the design of op-amps. The output of Class C amplifier is a highly distorted version of its input and hence it could not be used in applications like audio amplifiers which require high fidelity. Fidelity refers to reproduction of frequency content that exists in the input signal. Fidelity is low for Class C amplifiers. So, distortion. These are widely used in high power, high frequency applications such as radio frequency transmitter. So far, our discussion has been on traditional classes of amplifier operation: class A, class B, class AB, and C. Now we move a little ahead and discuss some of the modern or semi-modern classes of power amplifiers. We begin the discussion with class D. Class D amplifiers use pulse width modulation, pulse density modulation, or some advanced modulation form. Their operation is the input signal is converted into a sequence of higher voltage pulses, output pulses. The frequency of the output pulses is typically 10 or more times the highest frequency of input signal. The output pulses are then applied to a low pass filter to eliminate the pulse frequency and its harmonics. The resulting filtered signal is then amplified replica of the input. So operation involves conversion of the input signal into pulses. They are then filtered to eliminate pulse frequency and its harmonics. After filtering, the resultant signal is the required amplified input. The term class D is usually applied to devices intended to reproduce signals with a bandwidth well below the switching frequency. The main advantage with class D amplifiers is their power efficiency. So a point to be noted is here. In addition to class A, B, AB, and C, there exist other classes like D, and some more we are going to see in the next slide. Class D applications. Compared to an equivalent class AB device, a class D amplifier's lower losses permit the use of a smaller heat sink for the MOSFETs while also reducing the amount of input power required, allowing for a lower capacity power supply design. This class of amplifiers has been widely used to control motors, but they are also used as audio power amplifiers presently, with some extra circuitry to allow analog to be converted to a much higher frequency pulse width modulated signal. So to control motors, class D operation is used, also used as audio power amplifier. High quality class D audio power amplifiers have now appeared as rivals to traditional AB amplifiers in terms of quality. An early use of class D operation was as high power subwoofer amplifiers in cars, relatively inexpensive in comparison to class AB amplifiers. So class D is more efficient, less expensive when compared to class AB. As already mentioned, several other classes are also there. Here we consider class EF, class GH. Doherty is also there. Some important points regarding these classes. Class EF amplifiers are highly efficient switching power amplifiers. They are used at such high frequencies where switching time becomes comparable to duty time. So they are high frequency switching power amplifiers. Class EF. Class GH amplifiers are a variety of designs that enhance the performance of class AB output stages with the greater efficiencies and lower distortion levels. These designs are quite common and essential in large audio amplifiers since with inefficient amplifiers, large heat sinks and power transformers, which may be prohibitively costly, are required to be used. These classes G and H are used. Doherty amplifiers are a hybrid configuration consisting of a class B primary or carrier stage in parallel with a class C auxiliary or peak stage. These are able to give more efficiency, more than 60%, whereas earlier designs give only less than 50%. With this, we come to the end of the session. In this session, the focus is on class B operation, class AB operation, class C operation, their functioning, standard circuits, and their applications. Hope this session is useful to you. We meet again in another session with a new topic soon.